Hello friends, today we are going to read about the chapter of organic chemistry diazonium salt from the Pradeep publications. Introduction. Arene diazonium salts were discovered by John Peter Graces in 1858. They have the general formula Ar2X negative, where Ar stands for the aryl group and X may be any anion such as Cl negative, Br negative, NO3 negative, HSO4 negative, BF4 negative, etc. Aliphatic diazonium salts are also known, but they are highly unstable. They rapidly decompose even at low temperatures, forming carbocations and nitrogen gas. Therefore, in this unit, we shall discuss the chemistry and synthetic application of arene diazonium salts only, particularly with reference to benzene diazonium chloride. Now we will read about nomenclature. Diazonium salts are named by adding the suffix diazonium to the name of aromatic compound followed by the name of anion. Now, structure of benzene diazonium chloride. Molecular formula. The molecular formula of benzene diazonium chloride is determined from analytical data and molecular weight determination is C6H5N2Cl. Grace's structure. Grace's proposed structure for benzene diazonium chloride, in which both the nitrogen's atom were directly linked to benzene nucleus. This structure, however, failed to account for the following facts. Its salts like character, displacement of both the nitrogen atoms by a univalent atom or group in most of its reactions. Its reduction to phenyl hydrazine, in which only one nitrogen is attached to benzene ring. Formation of azo compounds by coupling reaction. Fifth one is formation of aromatic diazonium salt from penta-substituted anilines. Kekulé structure. Kekulé proposed structure for benzene diazonium chloride, in which one nitrogen was linked to the benzene nucleus. C6H5 N double bond N Cl. Evidence in favor. Structure. Second, explain most of the drawbacks of Grace's structure. First, such as the reduction to phenyl hydrazine, formation of azo compounds by coupling reaction, preparation of diazonium salt from penta-substituted anilines, and displacement of both the nitrogen atoms by a univalent atom or group. Points against Kekulé structure. Structure. Second, cannot explain its salt-like character and instability as compared to azo compounds, since both contains N double bond and linkase. Bloom-Strand structure. Bloom-Strand suggested structure for the benzene diazonium chloride, in which the nitrogen attached to the benzene ring is pentavalent while the other is trivalent. Evidence in support. It explains all the objection of structure 1 and structure 2nd and 3rd is further supported by the following facts. Its ready solubility in water but not in common organic solvents. Its complete ionization as shown by conductivity measurements. The presence of a triple bond as shown by infrared spectroscopy. Its instability as compared to azo compounds. It explains the geometrical isomerism as shown by diazotates or diazoates, which are the metallic salt of diazonium hydroxide. The sodium benzene diazoate can exist as a pair of geometrical isomers due to hindered rotation about the N double bond N bond. Preparation of diazonium salt. Aromatic diazonium salts are generally prepared by adding a cold aqueous solution of sodium nitrite to the solution or suspension of a primary aromatic amine in an acid at 273 to 278 Kelvin. ArNH2 plus NaNO2 plus 2HX treated with 273 to 278 Kelvin N positive triple bond NX negative plus NaX plus 2H2O. Arene diazonium salt. Diazonium salts are also formed when aromatic primary amines react with nitrite esters such as amyl nitrate. The nitrate esters needed for the purpose are prepared by treatment of alcohol with nitrous acid. The process of conversion of a primary aromatic amine into its diazonium salt is called diazotization. General procedure for diazotization: the primary aromatic amine is dissolved or suspended in a dilute acid such as HCl H2SO4. 3 mole of acid are generally used for every mole of the amine to be diazotized. 1 mole to form the salt of the amine, 1 mole to liberate nitrous acid from sodium nitrite, and 1 mole to keep the reaction mixture acidic enough to suppress the undesirable side reactions such as coupling of the diazonium salt thus formed with the free amine. The amine solution is cooled and a cool aqueous solution of sodium nitrite is added slowly to it at such a rate that the temperature of the reaction mixture does not rise above 278 Kelvin. The addition of sodium nitrate solution is stopped as soon as a few drops of the reaction mixture produces a blue color with starch potassium iodide vapor showing the presence of unreacted nitrous acid in the reaction mixture. Too much excess of nitrous acid is generally avoided since it subsequently interferes with the reaction of diazonium salts. The excess of nitrous acid may be destroyed by the addition of urea. Since diazonium salts slowly decompose even at low temperature 273 Kelvin to 278 Kelvin, they are used immediately after preparation. The mechanism is supported by the observation that aromatic amines containing electron withdrawing groups such as NO2 are less easy to diazotize. This is due to the reason that the nucleophilicity of amino group is reduced due to electron withdrawing effect of NO2 group. As such amines can however be diazotized in acetic acid. Conversely, aromatic amines containing electron donating groups at ortho and para positions, example O-toluidine, P-anisidine, undergo diazotization much more readily than aniline. Stability of diazonium salts. Aromatic diazonium salts are much more stable than aliphatic diazonium salts due to the dispersal of positive charge over the benzene ring. Alternatively, the instability of diazonium salt is due to their tendency to eliminate an exceptionally stable molecule of nitrogen to form carbocations. Since the phenyl or aryl carbocation is much less stable than alkyl carbocations, therefore aromatic diazonium salts have much lower tendency to eliminate nitrogen than aliphatic diazonium salt. In other words, aromatic diazonium salts are much more stable than aliphatic diazonium salts. Now we will read about physical properties. Arene diazonium salts are generally colorless, crystalline solids, highly soluble in water. Many diazonium salts, especially nitrites, are dangerously explosive in the dry state. Therefore, they are never isolated but are usually prepared in situ and used immediately after their preparation. However, certain diazonium salts, such as fluoroborates, are relatively insoluble in water and are stable enough to be dried and stored. Some diazonium salts also form complexes with metallic salts, such as zinc chloride, example ArN2 positive, ZnCl4 2 negative. These complexes are generally insoluble. Now we will read about chemical properties. Arene diazonium salts are highly reactive compounds. Their high reactivity arises due to excellent leaving ability of the diazo group as nitrogen gas N2. They are therefore extremely useful synthetic reagents in organic chemistry. The reaction of diazonium salt are broadly divided into two categories: reactions in which the diazo group is replaced by monovalent atoms or groups, reactions in which the nitrogen atoms are retained. Reaction in which the diazo group is replaced by monovalent atoms or groups. Some important reactions of this category along with their synthetic applications are discussed below. Replacement by hydrogen deamination. The replacement of diazo group by hydrogen or the reduction of diazonium salts to arrange hydrocarbons is usually brought about by treating a diazonium salt with hypophosphorus H3PO2 acid at room temperature, preferably in presence of Cu first salt as a catalyst. Arraign diazonium salt plus H3PO2 plus H2O is treated with Cu positive ARH plus phosphoric acid plus HX plus and 2 gas is released. This reaction can also be carried out by treating amines with sodium nitrite and hypophosphorus acid as diazotizing reagent. Alternatively, diazo group may be replaced by hydrogen by heating arraign diazonium salts with ethanol. For example, the whole process involving the diazotization of an amine followed by reduction of diazonium salt or replacement of the diazo group by hydrogen is called deamination. It may be emphasized here that during the reaction of diazonium salt with ethanol, two products are usually obtained, one involving the replacement of the diazo group by hydrogen as discussed above and other by the ethoxy group. The relative amounts of the two products, however, depends upon the nature of diazo compound and the alcohol used. If a first group is present in the nucleus and ethanol is used, the replacement of diazo group by hydrogen predominates. If on other hand methanol is used, predominant product is aryl methyl ether, that is anisole. Benzene diazonium chloride plus CH3OH gives anisole plus N2 plus HCl. Mechanism: synthetic applications. The importance of deamination is illustrated by the following application: synthesis of M-bromotoluene. P-toluidine is treated with CH3CO2O pyridine acetylation gives p-methyl acetanilide is treated with Br2CH3COOH, that is bromination reaction gives 2-bromo 4-methyl acetanilide. Then 70% H2SO4 and heat, this is hydrolysis, gives 2-bromo 4-methyl aniline. Now we will do diazotization, that is NaNO2 HCl 273 to 278 Kelvin temperature. CH now M-bromotoluene is formed. Recall, M-bromotoluene cannot be prepared by direct bromination of toluene or Friedel-Crafts alkylation on bromobenzene due to ortho-para-directing nature of methyl group and the bromine atom. Replacement by hydroxy group. Synthesis of phenols. Diazonium salts react with water in presence of acids to form phenols. The reaction is generally carried out by adding the solution of a diazonium salt to a large volume of boiling dilute sulfuric acid. The acidic conditions minimize the side reaction involving the coupling of phenol with diazonium salts. Synthetic applications. This reaction is especially important since only a few methods are available for direct introduction of a hydroxy group into benzene nucleus. Synthesis of M-nitrophenol. M-nitroaniline is treated with NaNO2 H2SO4 at the temperature 273 to 278 Kelvin. Diazotization gives N2HSO4 benzene ring NO2 treated with dilute H2SO4 boiling OH gives M-nitrophenol replacement by halogen. Different methods are used depending upon the halogen to be introduced. Replacement by chlorine or bromine. Sandmeyer reaction. Aryl chlorides or bromide can be easily prepared by treating a freshly prepared cold aqueous solution of an arene diazonium salt with solution of cuprous chloride in hydrochloric acid or cuprous bromide in hydrobromic acid. This reaction is called Sandmeyer reaction and gives aryl halides in 60 to 80% yield. Gutterman reaction. It is a modification of Sandmeyer reaction in which copper powder and a hydrogen halide are used instead of cuprous halide dissolved in the corresponding hydrogen halide. Yields are often lower, around 40%, than those obtained by Sandmeyer reactions. Replacement by iodine. The replacement of the diazo group by iodine does not require cuprous halide or copper as a catalyst. It is simply achieved by treating a diazonium salt with potassium iodide or a solution of iodine in potassium iodide. Replacement by fluorine. Wals-Sakkiman reaction. When an aqueous solution of a diazonium salt is treated with fluoroboric acid, diazonium fluoroborate gets precipitated. It is filtered and dried. Unlike other diazonium salts, diazonium fluoroborates are fairly stable compounds. When dry diazonium fluoroborate is heated, it decomposes to produce aryl fluoride and boron trifluoride. Replacement by cyano-CN group synthesis of nitriles. Aryl nitriles can be prepared by treating a diazonium salt with cuprous cyanide or potassium cyanide and copper powder. To avoid the loss of cyanide as HCN, the diazonium salt solution is first neutralized with sodium carbonate and then treated with cuprous cyanide. This reaction is also modified Sandmeyer reaction. Synthetic applications. Since hydrolysis of nitriles give carboxylic acids, therefore synthesis of nitriles provide us with an excellent method for the preparation of carboxylic acid from nitro compounds. Replacement by nitro NO2 group. Nitro compounds are generally prepared by treating an arene diazonium fluoroborate with an aqueous solution of sodium nitrile in the presence of copper powder. Replacement by an aerosonic acid ASO3H2 group. BART reaction. Treatment of an arene diazonium salt with sodium aracinate in presence of copper sulfate followed by acidification gives an arylosonic acid. Replacement by an aryl group. Gomberg-Bachmann reaction. When an arene diazonium salt is treated with an aromatic compound, liquid or its solution in an inert solvent if solid, in presence of an aqueous alkali, biaryls are formed. Yields are usually less than 40%. Mechanism. The reaction is believed to occur by free radical mechanism. In alkaline medium, diazonium salts are converted into corresponding azo compound with decomposed to produce aryl radicals. Reactions in which nitrogen is retained. Reduction to aryl hydrazines, arene diazonium salt upon reduction gives good yields of aryl hydrazines. This reduction can be brought about by a number of reagents such as a stannous chloride, hydrochloric acid, sodium sulfite, sodium hydrosulfite, and even electrolytically. If, however, strong reducing agents such as ZnHCl is used, the product is an aromatic amine. Mechanism of reduction of diazonium salt with sodium sulfite. The reaction probably occurs through nucleophilic attack by the sulfur atom of the sulfide ion on both the nitrogen atom, forming the dianion of hydrazine sulfonic acid, which is then converted into hydrazine in presence of acid. Coupling reactions. Arene diazonium salts react with highly reactive, that is electron rich, aromatic compounds such as phenols and amines to form brightly colored azo compounds. This is known as coupling reaction and is extensively used in azo dye industry, whereas coupling with occurs in basic medium pH 9 to 10, that of amines occur in faintly acidic medium. Coupling usually occur at para position with respect to OH or the NH2 group. If, however, the para position is, it occurs at ortho position. If a compound contains both an amino group as well as hydroxy group at para position with respect to each other, then the orientation of coupling reaction can be changed by changing the pH of the medium. The well-known indicator methyl orange, which is widely used in acid-base titration, is obtained by coupling the diazonium salt of sulfanic acid, the N-dimethyl aniline. Mechanism of coupling reaction. The coupling reaction between benzene diazonium chloride and phenols or amines is an example of electrophilic substitution reaction in which diazonium ion act as the electrophile while phenol or amine act as nucleophile. Coupling with phenols. Since benzene diazonium ions are only weakly electrophilic, therefore strong nucleophilic are needed for the reaction to occur. Further, since phenol is weakly nucleophile but phenoxide ion is strongly nucleophilic, therefore coupling reaction of phenols are usually carried out in alkaline medium. Role of pH. The pH of medium plays an important role in the coupling of phenols as stated above. Coupling of phenol is carried out in the weakly basic medium as explained above. In the alkaline medium, the diazonium salt first forms diazonium hydroxide, which immediately rearranges to diazohydroxide, which further reacts with alkali to form the corresponding salt called the diazotate. All these three species in fact exist in equilibrium. Since at high concentration of OH negative ions, the equilibrium will shift in favor of diazohydroxide and diazotate, both of which do not couple. Therefore, for the desired coupling reaction to occur, the pH must be kept as low as possible in alkaline medium. However, a too low pH would suppress the dissociation of phenol to phenoxide ion. Therefore, to carry out the coupling reaction, an optimum pH is needed. In actual practice, the optimum pH for such coupling reaction is between 9 to 10. Coupling with amines. Tertiary amines. The mechanism of coupling reaction of diazonium salt with tertiary amines is similar to that of phenols, except that this coupling is carried out under weakly acid conditions. Reaction with primary and secondary amines. Coupling of diazonium salt with primary or secondary amines occurs in neutral or mildly alkaline medium. Here, NH2 group of amine first attack the diazonium cation to form diazoaminobenzene. However, when the diazoaminobenzene thus formed is heated in presence of acidic medium, it undergoes diazoamino-amino-azo rearrangement to form p-aminoazobenzene by following mechanism. Role of pH in the presence of a high concentration of H positive ions. The lone pair of electrons on the N atom accepts a proton. As a result, the amine exists predominantly in the protonated form. Due to the absence of a lone pair of electrons on nitrogen atom, the amine is no longer nucleophilic and hence the coupling reaction will not occur at a high concentration of H positive ion, that is low pH further as. Thank you.